Well, it's my pleasure to welcome Anna Wienhard here in Bendlevo, in the spirit, let's say. Anna Wienhard is one of 4 directors of the Max Planck Institute in Bonn. Before, she was a professor at the University of Heidelberg and director of the research station Geometry and Dynamics, and at the same time research group leader at the Heidelberg Institute for Theoretical Studies. In Heidelberg, she was also involved in a research cluster funded by German Science Foundation, structures a unifying approach to emergent phenomena in the physical world, mathematics, and complex data. Her research interests are in discrete subgroups of Lie groups, deformation spaces, Anosov representations, and higher Teichmüller theory. She gave a plenary talk at the European Congress of Mathematics in June in Spain. She's also editor in a few highly respectable mathematical journals. She got her PhD in 2004, and then she spent years 2005, 2012 in Princeton, both at the university and at the Institute for Advanced Study. Anna, please, the floor is yours.
Thank you very much, and thank you very much for the invitation. It's really, for me, a pity that I cannot be there in Bendlevo. I have very good memories. One of the first conference I went to right after my PhD was a conference in Bendlevo, and I started a collaboration with a colleague of mine with whom I still collaborate, and I still have very fond memories of some of the discussions and interactions at the conference. So it's a place which has a special place in my heart. I want to just correct one thing you said in the beginning. So I'm director at the Max Planck Institute, but not in Bonn. So there are 2 Max Planck Institutes for Mathematics in Germany. So the one in Bonn and the Max Planck Institute for Mathematics and the Sciences in Leipzig. And I'm based in Leipzig and not in Bonn.
Okay, so, I'm very sorry.
No problem. So what I want to do, or try to do in my talk, is in a nutshell to do the following. So I want to tell you a little bit about hyperbolic manifolds and what hyperbolic manifolds have to do with discrete subgroups of matrix groups. So in particular of the group SO1N, so matrices which preserve a symmetric bilinear form of signature 1N. And then I want to tell you, so first I tell you a little bit about this hyperbolic picture, and then I want to tell you a bit about recent developments in the study of discrete subgroups of more general Lie groups, so in particular more general matrix groups, like the group of n by n matrices of determinant 1, where the size of the matrix can be arbitrarily large, or the symplectic group, so linear transformation which preserve a skew-symmetric non-degenerate bilinear form. And then we will encounter the two notions which appeared in the title, the notion of Anosov representation and higher Teichmüller spaces. But now I want to first go and look at hyperbolic geometry, and I will focus on dimension 2 and dimension 3. So I don't know what you know about hyperbolic geometry. So it was for many centuries not clear whether there is something like hyperbolic geometries, or like a geometry which satisfies all of Euclid's axioms and postulates except the parallel axiom. So what we know from Euclidean geometry, that if we have a line and a point, there's a unique parallel line through that point. In hyperbolic geometry, there are infinitely many parallel lines through a point which does not lie on a given line. And this was a quite a revolution in geometry, and hyperbolic geometry plays an important role in all kinds of areas of mathematics now, in physics. It developed further. It actually might be interesting and perhaps not so well known is that actually in the last, I would say, 7 years or so, it became also quite popular to some extent in machine learning and in somehow machine learning tasks where you look at embeddings of graphs or data points in hyperbolic space, not in Euclidean space. I will not say much about that, but I mean, keep that in mind. And if you find this interesting, you can research a bit about that before. So what's the hyperbolic plane? So as a space, we can think of the hyperbolic plane in the following model. We take as its point the interior of a disk of unit radius. And we think of this as a disk sitting in just R2, but now we change the Euclidean metric by a factor, conformal factor, which makes distances which are close to the boundary and which are very short in the Euclidean distance, very long in the hyperbolic distance. So this rescaling of the metric has the effect that this interior of the disk is actually an infinite diameter space, and the boundary of the disk, the circle, actually lies at infinity. So this is not part of our space anymore. If you look at the so this, you can check this is a Riemannian metric. If you compute the curvature, it has constant curvature -1. And if you look at the group of isometries, so the group of transformations of the interior of the disk, which preserves this metric, you can realize it as the group of 2x2 matrices with determinant 1, where the matrix, the identity matrix, and the minus the identity matrix act precisely the same way, so you quotient out by them. That's what we call PSL2R. So there's a similar model in 3 dimensions. So now instead of taking the interior of the disk, we take the interior of a the interior of a 2 sphere, so a 3-dimensional ball. And again, you endow it with a metric, which is a rescaling of the Euclidean metric, where if you go closer to the boundary, you rescale by a factor so that distances which are short for your Euclidean eye are actually long in this hyperbolic metric. And if you look at the group of isometries, now one way to realize it is as 2x2 matrices over the complex numbers. There is also another way to realize it as I had on my first slide, as the group SO13, so as matrices which preserve the signature, quadratic form of signature 1, 3. So let me describe to you another model for the hyperbolic plane, so for the 2-dimensional hyperbolic space. So we had the disk model. So there's another very important model, which is called the upper half plane model. So for this, we think of the complex plane, and we take just the upper half plane. So all the complex numbers where the imaginary part is positive. And then we can explicitly write down the action of the group of 2x2 matrices on this space, namely by fractional linear transformation. So if you have a matrix A, B, C, D, you apply it to a complex number Z, it sends Z to AZ plus B divided by CZ plus D. And for later reasons, I prefer often to think of this this matrix group SL2R, which is 2x2 matrix of determinant 1, rather as a symplectic group. So as 2x2 matrices, which preserve a skew symmetric non-degenerate bilinear form, which is given by this matrix 0, 1, -1, 0. So one other thing I want to emphasize, which is not so important for us now, but we will come back to that later, this action by fractional linear transformation does not just give you an action on the upper half plane, it actually extends to the boundary, and the boundary is the real line plus infinity. And so this, it's even better to think of this as the real projective line, so that every point in there gives you a line in R2. And so this is another model of the hyperbolic plane. And I mean, depending on what problem you want to solve, sometimes it's useful to work in this model or in the other model. So now we want to, this is our model space, but now we want to combine this hyperbolic geometry on our model space with more interesting shapes, so with more interesting topological manifolds, and in particular with surfaces. So if you give me a surface which is oriented or orientable, has no boundary, then it's classified topologically by what's called the genus of the surface, which is just the number of handles or holes in your surface. So genus 0 is a sphere, and then if you take the sphere and you add a handle, you get a torus topologically. This is genus 1, and if you add more handles, you get something of genus G. And the geometric classification or uniformization theorem says whenever you give me a surface of genus G bigger or equal than 2, so glue at least 2 handles to a sphere, then it in a natural way arises as a quotient of the hyperbolic plane by a discrete group of isometries. And here's a picture of how you can think about that. So for the genus 2 case, so you take your surface of genus 2, and if you pick these loops, so you pick one for each hole, for each handle, you pick 2 generators which go around this hole, call them A1, B1, and for the other A2, B2. Then the fundamental group has this relation. If you cut the surface up along these curves, you get a 4G gon. And you can think of realizing now this 4G gon as a 4G polygon in the hyperbolic plane. And then you have the identifications which identify the edges, which give you isometries, which if you apply these, they glue together this polygon to give you your surface. So it's just a slightly more complicated version of taking a piece of paper, a rectangle, gluing 2 sides to get a cylinder, and then taking the cylinder, bend it, and glue the end circles together to get a torus. So this way, if you want, topologically, most of the surfaces you will encounter in your life, the natural geometry they carry is neither Euclidean nor spherical geometry, it's really hyperbolic geometry. Okay, so now if I give you one of these surfaces, you know you can endow it with a hyperbolic metric, or equivalently, you can realize it as a quotient of the hyperbolic plane. But there's actually not just one way to do it, but there's many different ways to do it. And we like to study the space of all possible ways to take this fixed topological object and put a hyperbolic structure, so a geometric structure on it. And we study the space of all possible ways of doing that. This is what's called the Teichmüller space, or also in this model, really the space of marked hyperbolic structures on the surface S of genus G. This is a nice manifold. It's actually homeomorphic to R to the 6G minus 6, and I will describe this in a little bit in the next slide, just shortly. One reason why it's a very important object, so it's a nice smooth object. At the same time, it covers a very singular object named the Moduli space of all Riemann surfaces. And since the Moduli space of all Riemann surfaces is an object which is really very important in many areas of mathematics and physics, whenever you look at structure on a 2-dimensional surface or a complex 1-dimensional variety, it actually pops up in many areas of mathematics. The way I want to look at, for most of the time, I want to look at this space of hyperbolic structures is I want to now strip it off the geometry. So we said, okay, so I can put a hyperbolic metric on the surface, or I can realize as a quotient of the hyperbolic plane. The only thing I want to remember of the surface is, in a sense, what is the symmetry group, the group of isometries, which I have to have acting on the hyperbolic plane, which gives me this hyperbolic structure. So the only thing I want to remember is a group homomorphism from the fundamental group of this topological surface here to the group of isometries of the hyperbolic plane, which, as I told you before, is the group PSL2R. So essentially 2x2 matrices of determinant 1. And if we do that, we can actually, there's a very nice description of the space of hyperbolic structures, just in terms of the space of homomorphisms. So the space of homomorphism itself has a topology. It's a space, it has singularities, it has connected components, and this, all the representations, all these homomorphisms, which I get from hyperbolic structures, they all sit in one connected component. And the way I get this connected component, I mean, every point in this connected component comes from a hyperbolic structure, which in particular means that this group homomorphism is an injection. So there's nothing in the kernel, and the image is a discrete group of isometries. So let me just very shortly say something about, I mean, how to see that this space of hyperbolic structures, Teichmüller space, is this 6G minus 6 dimensional ball, if you want, I mean, or vector space. I mean, it's not really a vector space, but affine space. So if you give me a surface and I want to try to put a hyperbolic structure on it, one strategy to do that is that I cut the surface into pieces on which I know how to put a hyperbolic structure on them, and then I glue it back together. And there are two ways, in some sense, to do that. So one is using pairs of pans. So you can take your surface and you choose simple closed curves, which are disjoint and which cut your surface into pieces which look like that. So like a Y, sometimes also called Y shape, or like a pair of pans. So if you have such a pair of pans, then there is an elementary result in hyperbolic geometry that you can put a hyperbolic structure on it. You have the freedom to choose the length of these three boundary curves. And when you choose the length of these three boundary curves, the hyperbolic structure is completely determined. And this actually, and if you never saw the proof, I mean, you go back to elementary hyperbolic geometry, it actually has to do with right-angled hexagons. So it really is about hyperbolic structures on right-angled hexagons. So now, on a pair of pans, if you give me the length of the curves, I have a unique hyperbolic structure. So now I can take just several pairs of pans and then glue them back together to get a hyperbolic structure on my surface. So here I would need two pairs of pans. So I have three parameters, the length of these curves. Then I can glue these two pairs of pans together. But when I glue, I have one additional parameter, because when I glue two circles, I can twist them. And so in addition to the length of this boundary circle, I also have a twist when gluing. So I get for each curve in my pair decomposition into pairs of pans, I get a twist and a length, or length and a twist. And so since, for topological reason, if you try to cut a surface of genus G into these pairs of pans, you need 3G minus 3 curves. And for each curve, you have two parameters. So you get this parameterization of the space of hyperbolic structures. That's called the Fenton-Nielsen parameterization. There's another way, and I just want to say it shortly, in which I explained just when you have a surface which now is not closed, but has one point which you could think of as a point at infinity. So here you see a one puncture torus. So this is the point you consider at infinity. This is the torus. Then you can take such a curve and cut it into triangles, but you want to cut it into triangles so that all the vertices of the triangles are this point which you consider at infinity. This we call ideal triangles. And so now there's again, so similar elementary result in hyperbolic geometry. If you take an ideal triangle, so a triangle with all three vertices at infinity, there's a unique hyperbolic structure on this. So if you cut your surface into these ideal triangles, every triangle has a unique hyperbolic structure, and now you just get a parameter when cutting two edges of the ideal triangle, because this is an infinite edge, so you can somehow shift it in order to glue it together. So this is another way to get the coordinates, and these are called shear coordinates, and we'll come back to that in a minute. But before that, I want to now, for one slide, forget completely about hyperbolic geometry, and give you a problem which originates as a problem in number theory, and then we will see what this has to do with hyperbolic geometry.
Sorry, may I have a question?
Yes.
So if you could go back to the to the slide. So you have explained that in order to cut these surfaces, we need 3G minus 3 closed curves. So
Yes.
those are not those red drawings, yes? These are not
Yeah.
curves.
So this is here, the genus is 2. So
Yeah.
3 times 2 minus 3 is 3. That's 1, 2, 3.
Yes, and for example, if the genus would be 3, then I don't see, according to this picture, how this would follow, this 3G minus 3.
Well, if the genus would be 3, so let me draw one here. 1, 2, 3, right? So you might
Yes.
want to do the so this here, this here, this here, this here, right? Then you have 4 curves, but
Yes.
then you don't have pairs of pans, right? If you took the other one upstairs, you have a 4-hole sphere. So you have, so if you wanted to cut this in a pair of pans, you have to take this curve and this curve. Now you have 6 curves, which
I
is
see.
3 times 3 minus 3.
Okay, okay, thank you.
Okay, so let me introduce this number theoretic problem. So it comes from Diophantine equation. It's called Markov number. So you have the following equation: x squared plus y squared plus z squared minus 3xyz is equal to 0. And you look for integer solutions, or positive integer. You need positive to solve that. Solutions of this equation. If you have a solution, you call it a Markov triple, x, y, z. And there's a famous result, which goes back to Markov, that all the Markov triples can actually be obtained by starting with the trivial solution, which everyone of you would find of this equation, namely 1, 1, 1, and then performing the following move. So if I give you a triple x, y, z, you obtain a new triple, a new solution of this equation by replacing x by y squared plus z squared over x and keeping y and z. And then I can permute them, because of course, if x, y, z is a solution, then y, x, z is also a solution. And then I can apply this move again. So this way you get all solutions to the Markov equation, and you can arrange them in this Markov tree. So you see here the starting of the Markov tree. You start with 1, 1, 1, then you get 1, 1, 2, 1, 1, 5. They are ordered so that the triple is by increasing numbers. So what does this have to do with hyperbolic geometry? So it actually has to do with hyperbolic structures on the surface which we just saw, the one puncture torus. So you take this one puncture torus, you cut it into 2 ideal triangles. So, and this is the combinatorial. So you have these 2 ideal triangles. So now you would like to measure the length of the sides of this triangle, but there's no length of the side because it's an infinite. It was an ideal triangle, so the side, both points are at infinity, so it's the length of the side is infinite. But you can measure it if you make some choice. You pick a small cycle here, which is called a Horner cycle, on your surface, and then each of these sides will cut this small circle somewhere, in the small disk somewhere, and then it comes back. And this is a finite part of your side of the triangle, and this is the number you measure in your hyperbolic metric. So if I give you a hyperbolic metric on a one puncture torus, and you pick a way of triangulating it with an ideal triangulation, and you pick this, what we call a Horner cycle, you can assign coordinates A, B, C to the sides. These are real coordinates, a priori. So now this choice of a triangulation is a choice you make. So you could make another choice. And one other choice, is that you take this triangulation and you flip the middle edge. So you replace this edge by this edge. And now you can, again, you do elementary hyperbolic geometry and see how does the length I measure of this geodesic change if I take this one. And it's given by the following formula. If your coordinates were A, B, C, and now you do the new coordinate A prime, It's given by the formula A times A prime is equal to B squared plus C squared. So if you rewrite it, making a flip in the triangulation, you make a coordinate change, which goes from ABC to the coordinate B squared plus C squared over ABC. And you see it's precisely the same transformation as we saw for Markov triples. So if we start with a hyperbolic structure where this length is 1, this length is 1, and this length is 1, we have one of the solution of the Markov equation. And then if we just change the triangulation of our surface, we get all the Markov triplets. You can also see in this, and I just want to point out shortly, in this, the Markov equation itself pops up because I chose this horse cycle, and this horse cycle has a certain length in the hyperbolic metric. But this length doesn't depend on how I parameterize this thing, because it doesn't depend on the triangulation I choose. If you compute what this length is, it's given by 2 times A squared plus B squared plus C squared over ABC. And this doesn't change when I flip and change the triangulation. So this is constant along this operation. If I start with 1, 1, 1, I see that the length of this horse cycle is 6. And if you plug this in, you get precisely back Markov equation. So there's a very nice interplay in this situation of the one-point factorials between these number theory and Diophantine, special Diophantine equation, Markov equations, and hyperbolic structures. Okay, so now we leave dimension 2. I want to just give you a little bit of, and this will be with much less detail, a little bit of insight in higher dimensions. So in particular, 3 manifolds. So where do hyperbolic 3 manifolds appear? So they play an important role in William Thurston's geometrization conjecture that every 3 manifold you can chop into pieces and then uniformize the piece. There are 8 geometries. One of them is hyperbolic geometry in 3 dimensions. And actually, to some extent, most 3 manifolds are hyperbolic. They also rise very naturally in other ways. So if you take a knot in space and think of this as sitting in a 3 sphere, and you take the knot complement for many knots, this knot complement naturally carries a hyperbolic structure. They arise when you have a special pseudo-Anosov diffeomorphism of a sphere, of a surface, and you glue a 3 manifold out of surface times interval and gluing it back. This has a hyperbolic structure. So they really appear in many different ways in dimension 3. There's one huge difference between dimension 3 and dimension 2. So in dimension 2, we saw if I give you a surface, then I can put one hyperbolic structure, which means I can take the fundamental group of this surface. I realize it as a discrete subgroup of the isometry group of the hyperbolic plane. And it's a discrete subgroup that the quotient is a compact manifold, a closed compact manifold. But then there are 6G minus 6 dimensional space of possibilities of doing that. In dimension 3, there's just one way. If you give me a hyperbolic 3 manifold, you give me its fundamental group, then by Mosto rigidity, there is a unique way to realize this fundamental group of this hyperbolic 3 manifold as a discrete subgroup in the isometry group of hyperbolic 3 space. So it's unique up to, of course, then I can act with an isometry, so I can conjugate this image, but there's no deformation space. So there's just a unique hyperbolic structure on a 3 manifold, if it has one. So this is very different, but still there's a rich, hyperbolic geometry in dimension 3 is rich in many other ways. And there is other richness when we don't ask for our discrete subgroup of the isometry group of the hyperbolic 3 space to be what we call a lattice. So to be a group which acts co-compactly on the hyperbolic 3 space. So this is the situation when we have a closed hyperbolic 3 manifold, but there are other situations where we can get discrete subgroups where the quotient, when we pass to the quotient manifold, this 3 manifold is not compact. It's not of finite volume, but it can be of infinite volume. So one important example of that is take the fundamental group of a surface. I realize it as a discrete subgroup in PSL2R by picking a hyperbolic structure. So now I can think of PSL2R as sitting in PSL2C. And so I can realize as a discrete subgroup in PSL2C. So this is like, if I do that and geometric in this picture, I have the hyperbolic 2 space, which is the interior of the equator sitting in the 3 ball. And my group would preserve that. If I take the quotient of the 3 ball by the surface group, which I now realize in PSL2C, it would the quotient will be topologically a surface cross an infinite, across the real line. So this is a very nice discrete subgroup, and it's even nicer that I can now take this discrete subgroup and deform it. So, I mean, having this discrete subgroup in PSL2R means I give you the fundamental group of a surface. So we had this AI, BI, and then there was one relation. So I basically give you 2G matrices in PSL2R, A1, B1, AG, BG, which satisfy a certain relation. But now I can slightly deform these matrices to make them complex matrices. And as long as I still satisfy this relation, I get a discrete subgroup of PSL2C, so of the isometry group of the hyperbolic 3 space, which is isomorphic to a surface. And small deformations of this will be called quasi-function groups. So they are defined in the following way. So they are defined by looking at infinity, in a sense. So you have a group which is, as an abstract finitely generated group, it's isomorphic to the fundamental group of a surface. And now you will have, you realize it as a subgroup of PSL2C. And if you look at, we look at what is called the limit set of this group. So what is that? So this is a subset at infinity of the hyperbolic 3 space, which we get by we take one point in the interior, any point X, and now you take this point and you let the group gamma act on this point. So you get an orbit. And this orbit, because I mean it goes to infinity, so it accumulates somewhere on the boundary. And what the limit set is really just, we don't focus on the orbit, but we just take the accumulation point. So we get some accumulation points on the boundary. So for quasi-function groups, this limit set has a very nice property, namely it's a quasi-circle. So it's homeomorphic to a circle, and it actually cuts the sphere at infinity in 2 pieces, which we call omega plus and omega minus. And then we can look at the surface group, our group gamma, acting on these 2 pieces. And these 2 pieces are now, topologically, they just look like disks. So the quotients of these 2 pieces will be, again, compact manifolds. It will give us 2 closed surfaces. But now they don't come with a hyperbolic structure because they're not modeled on hyperbolic space, but they come with what we call a complex projective structure, because you should really think of this 2-sphere at infinity as the complex projective line. And so you have this quasi-disks, which are subsets of CP1, and you take the quotients, and so the surface naturally carries this structure. So this is a very important class of groups in these isometry groups of hyperbolic 3 space. They have one, if you look at this, having this limit set being a quasi-circle has one consequence, that if you look at the convex hull of the limit set in the interior, it gives you a convex set. And on this convex set, this group acts co-compactly. So the quotient of this convex set is preserved by this group action, and the quotient is co-compact. And so this now you can generalize in H3, hyperbolic 3 space, but actually in hyperbolic n space as well. So you look at discrete subgroups of the group of isometries, or I mean, you don't need to assume discreteness, it comes out in the end. You look at subgroups of the group of isometries, which have the following property, that there is a convex subset of your space, which is preserved by the group, and such that if you restrict the group action to this convex subset, you get a compact quotient space. And this is this group of convex co-compact subgroups. And this is a very important group in hyperbolic geometry. because what is well, let me tell you in a minute why they are very important. So they have very nice geometric properties. So I want to give you one other example of a group which is not convex co-compact, but which is of a bigger class of still nice discrete subgroups of the group of isometries, which are called geometrically finite. So they don't have a subset where they act co-compactly, but they have a certain, you can build a fundamental domain which has finitely many sides. There's a nice example where they also rise again from number theory, namely from what are called Apollonian circle packing. So it's the following problem. You take the disk, so think of it as one circle. So now you want to inscribe 3 circles which are mutually tangent. And then when you do that by the theorem of Apollonius, you can, whenever you have these 3 mutually tangent circles, there's a unique 4th circle you can add. So you can start with these 4 mutually tangent circles and then add further circles. So you get what's called an Apollonian circle packing. So you think of this as sitting in C, or CP1 rather. And then you can look at the group of isometries, or not isometries, of symmetries of this packing. This gives you a discrete subgroup of PSA2C. And this is called the Apollonian group. And this is an example of what we call a geometrically finite Kleinian group, not a convex co-compact one. So it still has some nice geometric properties, but not as nice as these convex co-compacts. So here's what I described to you a little bit, this landscape of discrete subgroups in hyperbolic geometry. So you have this, you have subgroups which we don't understand, which are very wide. And then we have this class of geometrically finite subgroups. In there, we have 2 special subsets, namely the set of co-compact lattices, so discrete subgroups where the quotient is co-compact of the entire ball, and non-co-compact lattices, which are discrete subgroups where the quotient of the ball has finite volume but is not compact. And then you have in between this set of convex co-compact subgroups, which is a much bigger class than lattices, the co-compact lattices. So these are these groups which preserve a convex set on which they act co-compactly. So why are these convex co-compact subgroups so interesting? So one is they are what we call dynamically stable. So which means I described to you before, if you take a subgroup in SZ2R, think of it in SZ2C, you can deform it. So the same you can do also with a convex co-compact subgroup. If you take a convex co-compact subgroup and you deform it a little bit, then it's still convex co-compact. So if you just deform it a little bit, you know it stays convex co-compact. That's why this class is particularly nice, because if you think of it in terms of this space of homomorphisms, where we embed a Teichmüller space in the space of homomorphisms, we think of these convex co-compact subgroups as homomorphisms into the isometry group of the hyperbolic free space. It gives you an open subset of the space of homomorphisms. The other is they have nice metric properties. So if you measure, so you have your finitely generated group, you can think of putting a metric on this group by just fixing some set of generators. If you have an element, you measure how many generators do I need to write this element, and this gives a metric on the group. And for convex co-compact subgroup, this metric on the group is by Lipschitz with so additive and, so it's quasi-isometric, so it's, you have a by Lipschitz constant and an additive error to the metric you would get by looking at the orbit of the group in a hyperbolic free space and just restricting the distance you measure in a hyperbolic free space. So these are what we call quasi-isometric embeddings, and this is actually any quasi-isometric embedding in hyperbolic into the isometric group of a hyperbolic n-dimensional space is a convex co-compact subgroup. They give rise to interesting geometric structures on manifolds, and I shortly described this to you for this quasi-function case. And there are nice relations between growth of orbit. So if you count how many orbit points you have in growing balls in hyperbolic free space, and the Hausdorff dimension of the limit set. So there, a priori quantities which have nothing to do with each other, which you can relate for convex group compact subgroups. And one which I will not tell you anything about in detail, you can actually use then this variation of Hausdorff dimensions for convex group compact groups, and for example, for quasi-function groups, to use it to write down a metric on Teichmüller space. So they rise in many interesting ways. So this is basically this kind of glimpse into hyperbolic and manifolds and discrete groups and their isometry groups I wanted to give to you. So now we want to go and leave the world of hyperbolic geometry. So we want to leave the world of constant curvature -1. And in particular, we want to leave the world of negative curvature. So we want to look at groups, which are more general Lie groups, or more general matrix groups, and where the spaces we naturally associate to them will have not negative curvature, but only non-positive curvature. So there might be subspaces which have 0 curvature, which look and are isometric to just Euclidean planes or higher dimensional Euclidean space. So here is basically now where you could take any non-compact reductive Lie group, and I want to focus on matrix groups. So just think of n by n matrices of determinant 1, or the group preserving of linear transformations on a vector space with a non-degenerate skew-symmetric bilinear form, or with a symmetric non-degenerate bilinear form of signature PQ. Or you could also look at the complex counterparts. So now I want to look at discrete subgroups of these groups, similar to before, where a discrete subgroup of PSA2R or PSA2C had a nice action on a geometric space, namely on the hyperbolic space of dimension 2 or 3. If you have a discrete group of such a more general matrix group, it has a nice action on what is called the symmetric space. So the symmetric space is defined in some sense most easily as a coset space. You take the group and you look at the maximal subgroup, which is compact. So for SLNR, this would be SON. And then you look at the quotient space. So this space has a nice Riemannian metric, and it has the property that if you look at the point reflection at every point, it's actually it extends to an isometry of the entire space. So I will give you an example of, more hands-on example of the symmetric space in a moment. But one of the key features is if I give you a discrete subgroup of this Lie group G, there's a nice non-positively curved space on which this group acts nicely, so properly, so that you can look at the quotient manifold or orbifold, so the quotient space, and this is a nice Hausdorff topological space. So now if we look at this discrete subgroups of Lie groups of higher rank, there again is two cases, so which we saw before. So one is gamma can be a lattice. So this means that if I look at this quotient topological space, it carries a volume form because it is a quotient of a Riemannian manifold. This has finite volume. And then there's this other case when gamma is not a lattice, where the quotient space is of infinite volume. So here are some of the examples of groups. So SLNR as mod SON, SP2NR mod UN, SP2NC. So there's this nice interesting dichotomy, which we call the rank 1 higher rank dichotomy, which looks at this symmetric space. If the symmetric space has negative curvature, this is when the group is of rank 1, and our hyperbolic 2 space, 3 space were in this class. Or this symmetric space has these planes or higher dimensional spaces of 0 curvature, and then it's called of higher rank. And so these higher rank symmetric spaces are very nice because they still very, described by matrix groups, so you can write down things very explicitly, but they have a much more intricate geometry than just hyperbolic space. And this, if you look at this picture on the left, this actually comes from a paper we wrote with people in machine learning and natural language processing, where somehow you can use these symmetric spaces to do graph embeddings or other data embeddings, and then somehow perform tasks in these symmetric spaces. But I'm not going to talk about that any further. So I want to give you one example of a symmetric space, very explicit example. And this is the example which generalizes the upper half plane model, which we saw for the hyperbolic plane. So for this, the group, the Lie group we are interested in is the symplectic group. So you have 2n by 2n matrices, which preserve this skew-symmetric non-degenerate bilinear forms. And these act, if you look at this, the symmetric space, look at what is called the Siegel upper half space model. So for this, instead of taking now the complex plane, we take symmetric n by n matrices with complex entries. So if n is 1, this is just a complex number, but now n can be bigger than 1. So we have a symmetric n by n matrix with complex entries. And we only look at those matrices where if we look at the imaginary part of this matrix, we have a real symmetric n by n matrix. This is positive definite. So now the symplectic group acts on this space again by basically fractional linear transformations, but now it's all matrices. So if I have a 2n by 2n matrix, which I write as a block matrix, so A, B, C, D are n by n matrices, Z is an n by n matrix, then the action is given by AZ plus B times CZ plus D inverse. So before we had divided by this number, but now we multiply with the inverse number. This action also extends to the boundary. So the boundary is now, I mean, the imaginary part can be 0. It can actually also be non-positive definite, but I want to focus on this most degenerate part. So the imaginary part can be 0. Then I have a symmetric n by n matrix, and I can go to infinity. And so now infinity, you should not think of one point, but as a very fat point. And so one geometric way to realize this boundary is to realize as a space of Lagrangian subspaces of the symplectic vector space. So we have R2n with this non-degenerate skew-symmetric form, and a subspace is Lagrangian if it's half-dimensional, so it's subspace of dimension n. But if I restrict this skew-symmetric bilinear form, it's a constant 0 on this subspace. I also want to just point out one important thing. So this is a symmetric space of higher rank, so we should see some of this Euclidean subspace of higher dimension. And this flat, so Euclidean subspace, you can see in this model as looking at just matrices, which are complex number times the diagonal matrix. If you take two of these matrices, they commute with each other. And if you look at this subspace in this Siegel upper half space, this will give you a Euclidean subspace of dimension n. So this, I mean, I chose this model because it doesn't look so much different than the upper half plane model for the hyperbolic situation. And I really want you to think of this as the hyperbolic plane or hyperbolic upper half plane, now not over the real numbers, but over the space of matrices or symmetric matrices. Okay, so now let me just recall, or I mean, tell you about some results in these higher rank Lie groups. So we saw going from dimension 2 to dimension 3 in hyperbolic geometry that we went from a rich moduli space, deformation space, to rigidity. So there was just one way I could take the fundamental group of hyperbolic 3 manifold and realize in PSA to C. So in higher rank, it's even worse. So there are two, or better if you want, I mean, there are two famous rigidity results. So Margulis superrigidity, and it implies Margulis arithmeticity. So it says, if you give me a lattice in one of these higher rank Lie groups, so an SLN R, when n is bigger or equal than 3, then no matter what representation you choose, no matter what group essentially you choose to embed your lattice into, there will always be a corresponding homomorphism of the ambient Lie group SLN. So it means that there's not just one way to embed the lattice as a discrete subgroup in SLNR, but no matter what other representation you choose, it all comes from a representation of SLNR. So there's nothing smart you can do with a lattice. And this has the consequence that any such lattice actually arises from a number theoretic construction. So it's what we call arithmetic lattices. And don't want to go into detail, but so essentially it tells you that, okay, so lattices, I mean, on one hand, of course, they have very interesting aspects to them, but from another perspective, they're really very boring because they almost look like the Lie group, just that you look at, instead of matrices with values in R, you look at matrices with values in the integers. Then it became even worse, or it becomes even worse when we look at this. So we saw in hyperbolic 3 manifolds, we went from lattices to this convex co-compact subgroups, and it gave us a much bigger class of groups. So if you do this in higher rank and you look at discrete subgroups, which preserve a convex subset of your symmetric space and act co-compactly on them, then Klein and Leeb and Jean-François Kahn independently proved that then gamma essentially has to be a co-compact lattice. So either you have, it preserves some subspace and then you have some rank 1 situation, so you're back in the negatively curved situation, or it really, the convex set has to be the entire symmetric space and you act co-compactly on the entire symmetric space, so you're a lattice. So this led the question actually, is there a nice class in this higher rank symmetric space, so in these groups like SLNR, is there a nice class of discrete groups which are not lattices, but which still have some structure and some geometric meaning and some structural properties? And so what basically developed in the past 25 years is that we have a very nice class of groups and a very nice theory, and this is the theory of Anosov representations. So now I want to tell you a little bit about these Anosov representations, and so you should really think of them as the right generalization of these convex co-compact subgroups in this setting of higher rank, in the setting of non-positive curvature and not negative curvature. And so so you can take any finitely generated group.
Well, excuse me, actually, a question.
Yes.
So all the time we have that the quotient has finite volume, yes?
No. It will be infinite volume.
It may be infinite volume.
So
right?
in these rigidity results tell you that, I mean, okay, so lattices, you assume finite volume. Convex co-compact subgroups already, a priori, they have could have infinite volume in the quotient, right? So they are not lattices. But if they don't preserve a subspace, so in the hyperbolic 3-manifold case, we had the first example where we preserve this disk spanned by the equator. Then you preserve a subspace, and then you have the quotient. But in high rank, if you don't preserve a subspace, but you move all over your space, if you are convex co-compact, then it means that you're lattice. So a priori, they could have infinite volume, but in the end, they don't. They even have a compact quotient. But what we really are after is you take any finitely generated group, you take one of these Lie groups, so SLNR, and you would like to look at discrete subgroups which topologically look like this finitely generated group, which act co-compact, and not co-compactly, but which just act properly on the space. And so the volume, if they are not lattices, the volume will be infinite.
Okay.
So in all these cases now, I want to discuss with Anosov representation, actually the volume will be infinite.
Okay.
So it turns out that the group, in order to have these Anosov representation, the group cannot be an arbitrary finitely generated group, but it has to be a group which has itself some negative curvature. So the group has to be what we call a hyperbolic group, which means that the group has some form of combinatorial negative curvature, and then it cannot be a lattice. So it will definitely always have infinite volume quotient. So let me give you the definition. So I want to tell you a bit about this Anosov representation, and then in the end, a bit of the special class of Anosov representations, which generalize this moduli space of hyperbolic structures. Let me tell you what Anosov representations are, and I just do it in SLN. So for this, there's one important object I have to introduce, and this is what's called the vector value distance function. So if you have a space and you have a group acting on the space, you can take a point, you fix a base point, you take gamma of the base point, and you can measure the distance between the point, the base point and its image under gamma. And then you get a number. In a symmetric space of higher rank, you can actually not just get a number, you can get a vector. And let me just, so you have a vector valued distance function. What this is, in the case of SLNR, is the following. So you give me a matrix in SLNR. I look at the singular values of this matrix. So these are the eigenvalues of G transpose G. I order them by size of the absolute value. I take the logarithm, and that gives me a vector. And this is the vector value distance function for the symmetric space for SLNR. So for other groups, there's a similar way you can describe them more theoretically. But so now let's take this vector value distance function. So this, because the matrix was determinant 1, right? If I do that, I get n numbers, but their sum is equal to 0. And on this somehow vector, I can, when I want to get a number, I can apply a linear form on this vector space to get a number. And there are special linear forms on these, again, coming from B theory, which are called roots. So which, I mean, if I look at the set of numbers here, lambda 1 to lambda n, where sum is 0, the roots just, and I will focus on the simple roots. So these assign to this vector the number lambda I minus lambda I plus 1. So they assign the difference of consecutive entries. And so now a representation, you call it alpha I Anosov, so where alpha I is this linear form. If you have two constants such that if you apply alpha I to this vector value distance function of x0 and gamma of x0, this is comparable, so bigger or equal than the norm of gamma in your metric on the group with respect to some generating set. Doesn't matter which generating set. So this means if you take a sequence in your group which goes out to infinity, so where this goes out to infinity, this vector value distance function goes out to infinity in a very peculiar way, because it means that the gap between the ith entry and the I plus first entry goes to infinity. So Anosovness gives you a very precise way of how elements in your group, when you look at their action on the symmetric space, can go to infinity. And so let me give you some of the examples of Anosov representation. So you get some examples in a similar way as we got these quasi-Fuchsian representations. So we take, for example, the fundamental group of a surface, we realize in SA2, and now we embed SA2 in SA3R. And so in SA3R, we can embed it just as a block. This is one embedding. Or you can embed it via the irreducible representation, and this gives you a different embedding. And these both give you Anosov representations, but they are have quite different properties. So the second one when you do this for SLN, it gives you what's called a Hitchin representation, and this is an example of these higher Teichmüller spaces. So let me give you properties of Anosov representation. So the one property I want you to remember, they are the right generalization of convex co-compact subgroups. But let's give you a few more, spell this out a little bit. So any Anosov representation is injective with discrete image. So you get as a result a nice discrete subgroup which act properly discontinuously on the symmetric space. This action has, as I said, gives you the quotient is a locally symmetric space. It will be, if you're in higher rank, always be of infinite volume. It has this nice property like convex co-compact subgroup that the orbit map is a quasi-isometric embedding. So measuring the distance in the group is related to measuring the distance on the orbit. And it has this dynamical stability. So if you give me an Anosov representation, I deform it a little bit, it's still an Anosov representation. So the set of Anosov representation actually gives an open subset of the space of all homomorphisms of the conjugation. And there's some dynamical aspect to it, which I don't have time to explain. And this Anosov representation actually You can think of them as reparameterizations of the geodesic flow on this hyperbolic group. I don't want to, this is very powerful, but I don't want to go into that. So now I want to just basically show you some slides. I mean, focus more on the picture and say one word about further properties and in some sense things we know about Anosov representation if we don't. So the quotient of the symmetric space by an Anosov representation is infinite volume. So in particular, it's not compact, but there are other homogeneous spaces on which you can find open subsets on which this group acts co-compactly. And so this is similar to this quasi-function example where you took the boundary at infinity and you had the upper disk and the lower disk, and the quotient gave you two compact surfaces. So this construction you can generalize widely to Anosov representations, and this gives you, for each Anosov representation, you get a compact manifold with a nice geometric structure on it. And actually, we now can prove in many cases this compact manifold actually has some relation to the hyperbolic group you started with. So if you take fundamental group of a surface, for example, or fundamental group of a hyperbolic n-manifold, this compact manifold is some fiber bundle over this hyperbolic manifold. What we don't know yet is, in just in very few cases, a finer understanding and finer properties of these geometric structures you get. So this is a topic of interesting current research. I told you for convex co-compact subgroups that there is this limit set, which is important. This is also a very important object for Anosov representations. And now things can happen which do not happen in negative curvature. So you can have a negative curvature, essentially the limit set can be smooth or fractal. In higher rank, the limit set can be also rectifiable, but not smooth. This can be C1 smooth, but nowhere C2. So there's a lot more phenomena happening. And you get, for some class of Anosov representation, a similar relation between orbit growth and Hausdorff dimension of the limit set. One thing which we don't understand at all, essentially, or just in one, actually, we're just starting to understand it. So we understand well in one case, but there's some partial understanding, partial case, is the space of Anosov representations. Because now you have an open subset of the space of homomorphisms, but it's usually not closed, only in very particular situations. And so what the closure of this space is, what happens when you go to the boundary, there are some interesting things happening, but we don't have really a good understanding of that. And so let me point out some and finish with that, some current and future directions. So one is, I mean, for an Anosov representation, I mentioned it, the finitely generated group has to be hyperbolic, but it's not known which hyperbolic groups admit Anosov representation. So there are some topological restrictions, there are some examples, but we don't have the complete picture. In hyperbolic geometry, we don't just have this class of convex co-compact subgroups, which we now generalize by Anosov representation. We also have geometrically finite. And so there are several works towards generalizing this class of geometrically finite subgroups in higher rank, but also there are a lot of open questions and not yet a fully satisfactory picture. You can do a lot of counting problems. So count, if you have an Anosov representation, count how many points you have in the orbit. It's related to interesting number theoretical problems. You can ask for more number theoretic properties of these finitely generated groups. So now they're not lattices, but they can still be defined. You can still find examples which are defined over some number field or have some nice number theoretic properties. You have this infinite quotient manifolds where there are tons of open questions regarding spectral properties of this quotient manifold. So whatever you know for lattices doesn't go through, but they are somehow, these Anosov representations are very tame so that we are starting to be able to see things. There's new work in going into the construction of explicit fundamental domains, which is very hard in higher rank because somehow bisectors, so hypersurfaces which have equal distance to 2 points in the space look really horrible usually. There's a work on how do you manage and walk around in the space of Anosov representation. So how do you write explicit deformations? And there's interesting group, which very recent work, which then connects also back to these quasi-Fuchsian representations when you look at complex groups and you ask for things like double uniformization theorems in higher rank. And so let me just end with the last slide that if you go to landscape in discrete subgroups in higher rank, I mean, the picture is much more complicated than in rank 1, but there's a lot of beautiful things happening and a lot of things which we still need to explore. Thank you.
Thank you very much. Okay, are there any questions or comments? Please. Okay, maybe people on Zoom, are there any questions or comments?
Can I ask a very naive question? Because in non-commutative geometry, we know the name Anosov because of Anosov foliations, and they generate type 3 factors. Am I right?
Yes. So here I gave you that, I mean, as a definition, what actually came as a later characterization of Anosov representation, which is the most concise way to, in some sense, state it. But the way, I mean, François Labrie, when he introduced the notion about 20 years ago, it was really looking at the dynamical system, in a sense. So you have this representation of your, and he looked at fundamental group of a hyperbolic manifold into your Lie group G. And now you have this representation, and now you build a bundle. So you can build the G bundle. Let's take just SLNR. You can take the Rn bundle, build the Rn bundle over this hyperbolic manifold. But now you lift this to the unit tension bundle. And once you lift it to the unit tension bundle, you have the geodesic flow of this hyperbolic manifold acting on that bundle. And so now the dynamical property is that if you look at this bundle over the unit tension bundle of your manifold, that this actually has an Anosov-like behavior. So you have a splitting of this bundle into two sub-bundles where one is exponentially contracted and one is exponentially expanded. So you really have, I mean, the lift of the geodesic flow to this bundle to some extent is an Anosov flow. And this is actually the picture where you see the dynamic stability is easiest seen in this picture, because now it just comes from dynamic stability of hyperbolic sets in this dynamical system. So this is the original definition really used this dynamical picture, and that's where the name Anosov representation in a sense comes from.
Okay, thank you very much.
Are there any other questions in the lecture room? Yes, please.
Okay, can you hear me?
Yes.
Okay, so I have like maybe a little weird question, but for the case of lattices in Lie groups, we can use this to construct many interesting manifolds with interesting topological properties due to certain theorems. For example, like this most of bundle that we have, for example, in case of solvable Lie groups. So can the study of Anosov representations also be used to find interesting topological examples of manifolds in the homogeneous spaces? Do you have some theorems that allows us to study that?
So I think yes. So, and I think, okay, so let me give you two answers to that. So one is the not so interesting one, but I mean, one is, so there are nice, for example, one thing you can do is for certain fundamental groups which come from nice constructions, more using lattices, but which are not lattices. So there are these Gromov-Thurston examples of, for example, negatively curved manifolds, which admit the metric of curvature arbitrary pinch to -1, but not a constant curvature metric. So all these can be realized also. I mean, you can write down Anosov representations of those, and then, for example, if you take the quotient manifold, you get some bundles. I mean, you get naturally as quotient manifolds some bundles over these Gromov-Thurston manifolds. So there is where there's a lot of things which arise when you build these domains of discontinuity, because actually, I mean, we have a very due to work of Kapovic, Leib, and Portier, we have a very systematic description of these domains of discontinuity associated to Anosov representations. And there are thousands of those. So, I mean, if you start writing them down by hand, you would write down particular certain ones. But for example, for SL4, if you are Anosov with respect to any root, I mean, all the roots at once, then there are more than 1,000 different domains of discontinuity. All the quotients are compact manifolds. And it's very hard to understand the topology of the quotient. So we worked very hard in a particular case. For example, when you take the fundamental group of a surface, you put it in via the irreducible representation into the symplectic group SP4R. Then you put this into SP4C. Then you look at one of the fundamental domains you look at the quotient manifold. You know by abstract arguments, it's a fiber bundle over the surface. But you have to work very hard to know what the fiber is. And in that case, you get that the fiber is CP1 connected some CP1 bar. And so when you look at these domains of discontinuity, there are many, many, many things which appear, and we have very little understanding of what their topology is.
Okay, thank you very much.
Okay, do we have some more questions? Okay, maybe let me check whether there is something on the chat. Okay, I don't see any question on the chat, so I think it's a time to thank our speaker again. Thank you, and I will stop recording.